At every scale of the universe, physicists are trying to answer one specific question: which objects interact with which other objects? Historically, we answer this by building models based on continuous geometry. We map out spatial coordinates, measure precise distances between bodies, and calculate physical angles. But when you look at extreme scales of complexity or zoom all the way down to discrete quantum states, continuous geometry can break down. The physical map often obscures the mechanics of the system. This image shows how the abstraction layer solves that problem. On the left, we have a physical system, a chain of atoms with spatial gaps. On the right, we strip away the physical form, reducing the system to a numerical network of nodes. This graphic demonstrates the primary rule: topology overrides geometry. Look at the straight line from A to C and the curved path next to it. In a graph, physical distances and angles are irrelevant. Unless explicitly coded, these represent the exact same topological connection. By removing the physical geometry, we isolate the topological connections. This allows us to investigate how the network structure might explain a system's behavior. For a wide range of physical systems, graph theory acts as a translation dictionary. Mathematically, a graph is built from vertices, labeled V. In a physical system, a vertex represents a particle, an atom, a node in an electrical circuit, or a discrete spacetime event. These vertices are connected by edges, labeled E. An edge translates to the physical interaction: an atomic bond, a force connection, a wire, or a causal path. Variables are attached to these edges to capture specific real-world conditions. Edge weights denote coupling strength, electrical resistance, or the energy cost of a transition. Adding directional arrows maps out the flow of a current or the forward movement of time. When those edges form a closed loop, a cycle, they translate directly into physical feedback paths or closed particle paths in quantum mechanics. Once a complex physical system is translated into vertices and edges, its motion, energy dispersion, and overall state can be calculated using a single set of matrix operations. We can test this by deriving the equations of motion for a macroscopic system of masses connected by springs using only their network connectivity. Imagine three identical masses connected in a linear chain by two identical springs. We render this as a three-node graph. To evaluate this mathematically, we use an adjacency matrix denoted as A. This maps exactly which node connects to which other node. Node 1 only connects to node 2, so its row in the matrix gets a 1 in the second column and zeros elsewhere. Node 3 also has only one neighbor, node 2, so its row reflects that single connection. The central node, node 2, connects to both node 1 and node 3. Its row in the center of the matrix gets two ones. Without measuring a single physical distance, the adjacency matrix has digitized the physical springs into a purely binary array. Next, we map the local density of the network using the degree matrix, labeled D. The degree matrix measures how many total connections touch an individual node, ignoring where those connections lead. Nodes 1 and 3 each have exactly one spring attached. We place a value of 1 in the top left and bottom right diagonal slots. Node 2 sits in the middle and is touched by two springs, so the center of our matrix diagonal receives a 2. Because the degree matrix only evaluates a node against itself, all off-diagonal elements are simply filled with zeros. We now possess two abstract maps: adjacency for the network shape and degree for the local density. Together, they contain the data needed to determine how energy will flow. These two matrices combine to form the central engine of graph dynamics, the graph Laplacian. This chart outlines the derivation. We calculate the graph Laplacian, L, by subtracting the adjacency matrix from the degree matrix. Look at the resulting pattern in matrix L. It features positive numbers running down the diagonal and negative ones in the off-diagonal positions. This illustration shows why that matrix dictates physical movement. The Laplacian dictates flow and acceleration by measuring how different a specific point is from the average of its direct neighbors. The classical second-order differential equation for a spring system states that mass times acceleration equals negative stiffness times displacement. We replace the continuous spatial parameters in that equation entirely with our discrete Laplacian matrix. By analyzing the eigenvectors of the Laplacian, physicists can extract the exact natural frequencies, the normal modes, of the physical system without ever drawing a spatial coordinate system. This connectivity also dictates behavior in statistical mechanics, where graph topology determines macroscopic material states. The Ising model maps atoms onto a lattice, where each vertex possesses a magnetic spin, pointing either up or down. The total energy of the system is determined solely by its edges. Connected neighboring spins either align with each other or oppose each other. In a state called antiferromagnetism, the interaction rule dictates that every node strongly prefers its neighbors to have the exact opposite spin. This diagram shows the paradox that occurs when we place that rule onto a triangular graph. If node A is up, node B must be down. Node C is now connected to an up and a down simultaneously, and is physically unable to satisfy both neighbors. This creates a mathematical paradox known as geometric frustration. The failure to reach a stable state is not a physical defect of the material. It is an inescapable mathematical paradox dictated entirely by the odd cycle topology of the graph. Network connectivity also models physical phase transitions through percolation theory. It asks, when do microscopic links randomly align to form a macroscopic path? This translates directly to the physical spread of forest fires, fluids flowing through porous rock, or electrical conductivity surging in disordered materials. Imagine a grid where microscopic edges have a small probability of opening. At low probabilities, we get isolated clusters. As probability increases, we hit a critical threshold. The clusters suddenly merge in a nonlinear leap, bridging the entire system. Physical state changes, like a sudden surge of conductivity, occur at the precise moment the graph becomes fully connected. This table summarizes the diagnostic toolkit, showing the scope of physical problems solved by this singular mathematical framework. The exact same graph Laplacian used to calculate the motion of mechanical springs is used to chart heat diffusing across a solid material. In quantum field theory, the infinite possibilities of particle scattering are organized by tracking allowed paths on a network. The causal structure of general relativity is modeled discretely using directed graphs. From mechanical vibrations and heat diffusion to quantum scattering and magnetic phase transitions, graph theory translates diverse physical interactions into organized networks. It provides a shared mathematical framework that reveals the connectivity at the foundation of these systems.